Okay, so in this session we're going to look at the force on a wire. So our key goal here is to be confident with the A2 level equations that you're going to have for the force on a wire. So what we have set up here in this diagram is something that should be pretty familiar to you guys by now. You've seen a lot of these types of things when we were doing the IGCSE. So what I have here is a power supply. So I could draw this if it was a battery. I'd always draw it with the larger side on this side. And so if you remember, we always, when we do this, we say that current goes from the positive side to the negative. So, to answer this question, you're going to be using Fleming's left-hand rule. So you make sure that you have your left hand, and then you have to remember the way that your fingers work with this. So I always do it as your first finger is the magnetic field, second finger is the current, and your thumb is the direction of the motion that it would try to have, so the force. So with this, you need to make your first finger for the field point from the north towards the south. Your second finger is going to go down, and so your thumb, as you will see, will be acting that way, so out of the page. Okay. That's Fleming's left-hand rule, and really, from IGCSE, that's about as difficult as it gets. So now we're going to go ahead and just make things a little bit trickier. So this is a classic experiment. This is the idea of a force on a wire. And what we have here is a piece of wire. And one of the key things about this is it has to be a stiff wire. Why stiff? It has to be stiff because I don't want that wire to just move up and down. I want that wire to be able to exert a force. So we have a yoke here. When we say the term yoke, we use that just to mean this actual metal plate. And we're saying that's holding two magnets. And I'm not sure, and I'm hoping it'll come out easily in the video, but the magnetic field should be going from this side, so I'd have this end of it would be the north, and the other side would be the south. Again, you have a battery designed here, so we have the positive side on this one. Remember, the tall one's always positive, so I've got a current going that way. Now what I've done is I've attached this to a top pan balance. So what we can do here is we can convert from a force to a, sorry, not from a force, we can convert, well, backwards and forwards between forces and masses. How does that work? Well, if you remember, we can say that a force on anything due to gravity, that is equal to mass multiplied by gravity. So what all a top pan balance is actually doing is it's measuring a force and reporting it as a mass. And we don't often think of it that way, but that's actually what it's really doing. It's measuring the force pressing down on top of it. So what we can do is we can reverse engineer this, and we say, well, therefore, whatever mass is displayed on the screen, that is equal to the force that's being applied to it divided by gravity, which would be 9.81. So in this case, we're going to assume that this is in grams, because that would seem reasonable. So we can work out, well, what is the apparent force due to this mass? So if it's reading 298.10 grams, then I can say that the force that is giving rise to that will be 0.2981, because we always want to convert into kilograms, multiplied by 9.81. So I can say that the force that this is actually recording, that is equal to 2.92. Let's just dispense with some of this. So this would be an equivalent to a force of 924 newtons. So if you think about Fleming's left-hand rule, you should straight away be able to work out the force on this wire. Follow it round, I can see that the current is travelling this way, so I want my first finger field, second finger current, so I can say that the force on my wire is pushing downwards. What that's going to cause is there's going to be a reaction force now, and I can say that my balance, if the wire is being pushed downwards, that's going to have a reaction force, and that's going to also cause a force on the top hand balance, because this wire can't go anywhere. Now you also notice that I've put in a variable resistor here. Why did I put a variable resistor? Well, because we can go ahead and look at how or what things will affect the the magnitude of this force. So with this setup, I can now record a force for a given current through my wire. And it turns out that, as a general rule, we get a pretty simple equation. Let's change it to something. Yeah, okay, there we go. Let's go with that. So I can say that the force that my wire experiences on it is equal to B times I times L. F is Bill. Whoops. What does that mean? Well, when I write it like this, I say that F is equal to the force on the wire. B is a magnetic field strength. So that is an intrinsic measurement of the field strength. When we go into stuff in more detail, we are going to call this a magnetic flux density. When we come on to look at generating electricity, that was what I was searching for, generating electricity, we will discuss this in way more detail. But for now, you can think of this as how many field lines per square meter are there. So the stronger the field, the stronger the magnetic field flux density. And we measure that in Tesla, which is a unit of a capital T. It's very confusing for physicists because we also use capital T to be the symbol for temperature. But when it's a unit, that means Tesla. And if you do this experiment, which I hope you will find that it also depends on the current in the wire, and it depends on the length of that wire. And hopefully some of those things will appear as sort of common sense type things to you. You should be able to see that if I have a longer wire, it's going to go through more field, more current, so the force will be bigger. So this equation stands absolutely to reason. Now what about in this instance? So that was pretty simple if we're doing IGCSE stuff. But what about now when I have a field that isn't at a right angle? Well, if you think about when you've done resolving forces, what we can say is, well, if I've got this particular length that I'm interested in, the part of it that's going to generate a force is the part of it that is acting at right angles to it. So what I can say is, well, what is the component of this length that is at right angles to it? So I hope you remember from your kinematics, I've got a measured angle here, theta, and we always measure that as the angle between the wire and the field line, so or as if I was going towards the field lines. So we use our zero theta would be going along the field lines. If I do that, then my equation becomes F is equal to B times I times L multiplied by the sine of theta. And that's, again, if you think about the stuff that we did in dynamics, that's because I'm stretching that angle out. I'm pulling out on theta, and that's stretching it to make it larger. So this equation is the full equation that you need for your A-level. Yeah, when we draw it, we say F is BIL sine theta. My pen is incredibly laggy, so I'm just going to leave it like that and not annotate anymore because apparently my tablet hates me. Alright, so let's just do a couple of past paper questions. Define Tesla. You'll notice this equation comes up lots of times in your IGCSE. So, we actually define that this way. We say it is the magnetic field strength required when a straight current carrying conductor with 1 amp, which is normal to, so perpendicular to a magnetic field, has a force per unit length of 1 Newton per meter. So it comes out of this equation, F is BIL sine theta. If I have a force of 1 Newton and a current of 1 amp, then, change that again. Let's say that my magnetic field strength is 1 Tesla. If my magnetic field strength is 1 Tesla, and I have 1 amp, then I can say that for every meter of wire, I'm going to have 1 Newton, assuming it is normal to or perpendicular to the magnetic flux density or the magnetic field lines. Because if that's the case, sine of theta becomes 90 degrees. So I'm saying that a 1 Tesla field at 90 degrees with 1 amp flowing through it will give me 1 Newton of force for every meter. So that's why you'll often see this written out in the exam. I would say, to be honest, if you just wrote it out in those words, you wouldn't likely get the marks. You have to make it really explicit and clear when you're saying it. That's set up around it. So here's another classic question. This is basically the same example I gave you earlier, but in CIE speak. So we have a stiff metal wire, and it says the magnetic flux density in the space between the poles of the magnet is uniform and 0 outside this region. That's important because if you think about a real magnet, we do know that they have some magnetic fields that come out around at the side, so it's going to cause some additional extra length. If you imagine that usually we're interested in this length here of it, because there's in reality some magnetic field out here, that would create additional force. But for your for your A level, they're never going to go that difficult, so they'll just say it's 0 outside it. They've given us a length, and I would go ahead and write this straight on, but I'm going to convert it as I go, so I can say that is 0.064 meters. Always worth, when you're annotating this on the exam, convert your units. It says when the current in the wire is switched on, the reading on the balance increases by 2.4 grams. The current in the wire is 5.6 amps. Calculate the magnitude of the magnetic flux density between the poles of the magnet. We can always start with our equation. F is equal to BIL sine theta. But it says that it's horizontally between it and it's uniform, so I can say that my sine theta, that's just going to be equal to 1. So this equation just becomes F is BIL. So that's why if you look at the mark scheme, they have just substituted in this way. Just so I get my writing out the way. So they've said, there's the... oh, sorry, I should have... I need to just add why they've done this bit. So it says here, they've multiplied 2.4 times 10 to negative 3. That's because we need to convert that into kilograms. So that will be 2.4 times 10 to negative 3 kilograms. And then they've just used the fact that force is equal to mass multiplied by gravity. So that gives you the force. And that's equal to magnetic field strength multiplied by, and they said it's 5.6 amps, so there's your I, and then your L is 0.64, so they've just done it as 10 to the negative 2. And when you plug that in, you find that that comes to 0.066 Tesla. That's actually a really, really high answer. Most magnetic field strengths, they're in the order of a few milli to micro or even nano Tesla most of the time. It doesn't normally go much higher than that. Also, just for exam technique, can you see that when they've written this out, they've actually put it in exactly the same order as it appears in the equation. So they've put in first the force, then the magnetic flux density, then the current, then the length. It's really important to do it in that same order just for consistency. Okay. Then it says that a low frequency alternating current is now passed through the wire. The RMS value of the current is 5.6 amp. Describe quantitatively the variation in reading of the current. So, what are we going to do? Well, if we think back to the stuff we did on AC, we can say that IRMS, that is equal to I peak, or let's say I peak, so the peak current, over root 2. So that then tells me that the peak current will be equal to, in this case saying that the RMS is 5.6, so that will be 5.6 multiplied by square root of 2. So I can go ahead and plug that into my equations, and what I would come out with would be plus 3g and minus 3.4g. So in other words, the maximum it will be is that, or the lowest it will be is below it. So they've done it here as saying that the new reading is 2.4 times root 2g. So the reason that they've done that is because they've said just by they've done it by inspection. Sorry. So they've said that in this case, because F is BIL, I'm not going to write it out because my pen's lagging, so it'll look really bad. But they're saying that okay, my current's gone up by a factor of √2. Therefore, my reading will also go up by a factor of √2. So they've multiplied by that factor of √2 to get the increase. Here's another good one. So we've got two wires next to each other. And it says that the wires pass through a horizontal card PQRS. So they're just identifying these corners to call it what it is. Says the current in wire X is 6.3 amps in the upwards direction. Initially there is no current in Y. Sketch in the plane of PQRS the magnetic flux pattern due to the current in wire X. So remember magnetic flux? We just call that the idea of the number of magnetic field lines. We'll go into this in more detail as we go through this. So go back to your IGCSE. We're thinking here about the field around a wire. So when we think about the field around the wire, we're going to use the right-hand grip rule. So that in the right-hand grip rule, your thumb is the direction of the current, and your fingers wrap round in the direction of the field. So what we're going to get is something that looks like this. Now, I'm not sure I'm going to be able to draw it properly because my pen really hates me, but I'm going to show it going anti-clockwise. So there's one. What's really important as we do this is to try and draw this getting further apart as we go. Now I'm doing an absolutely abysmal job of this because turns out paper, it's because my pen just keeps going, I'm sorry. Turns out paper's a lot better than this. In the mark scheme they wanted at least 4 and they must be getting further apart each time. Now the reason for that is that as you go further away from the wire, the field strength gets weaker exponentially. It goes over as a 1 over distance squared. So each time you go up, the field must get further apart. So if you come across a question like this, always remember to draw at least 4 field lines. I'm going to have a go at doing one more, even though it's going to be way outside where it should be, but hey, let's live dangerously. There we go. I mean, I would probably score 0 marks for that, but hopefully you can get a rough idea. You can see that they are getting further apart as they go. They are all concentric. And really importantly, you need to make sure that they're going all the way around. Lots of people end up drawing the arrows going to the right on both sides, so it's sort of like trying to almost go like that, which doesn't make sense. So you have to make sure that it's going anti-clockwise all the way around. So do lines at the top going one way, at the bottom going the same clockwise direction, but obviously in the other direction on the paper. Okay, so for part 3 it says the magnetic flux density B at distance x from a long straight current carrying wire is given by this expression. B is mu0 I over 2 pi x. So I is the current and mu0, this symbol here, that's the permeability of free space. Now, what does this mean? Well, if you were doing any other exam board, you'd have to learn this equation. But for CIE you don't, so don't worry about it. If you ever have to actually calculate it from a wire, they'll always give you the equation. But essentially, this permeability of free space, that just tells you how easy is it for a magnetic field to be set up in the wire. I is still the current, and then we have 2 pi multiplied by the distance. So that explains why when we're drawing it, we have to have these concentric rings getting further and further apart, because it's proportional to 1 over the distance, so B is going to get exponentially smaller every time you double your distance. So you're asked to calculate the magnetic flux density at Y. So it's very simple, we just plug it straight into the equation. I think the formula sheet for CIE, this is the absolute value of it. The CIE formula sheet says it's 4 pi times 10 to the negative 7. So when you plug that in, you get 6.3 as your current still, because there you have your 6.3 amps. Plug in the numbers to your calculator and you get 2.8 times 10 to the negative 5 Tesla, which is about right because remember we say that magnetic field strengths are always quite low. Then it says a current of 9.3 amps is now switched on in wire Y. Use your answer in part 2 to calculate the force per unit length in wire Y. Now lots of people can get themselves muddled up here, so it's very, very simple just to remember. I've already worked out the magnetic flux density at this point is 2.8 times 10 to the negative 5. So I can say at this point the magnetic field strength B is 2.8 times 10 to the negative 5 Tesla. So I don't need to do anything else. All I can do is plug it straight into F is BIL sine theta. Now they're both going in the same direction, so I can say that the magnetic flux density angle theta is 90, so this just becomes 1, so it just becomes BIL. I already know what the magnetic flux density is. I know my current, and I'm asked for force per unit length, so I want it per meter, so I'm going to use a length of 1 meter. When you plug that in, you get 2.6 times 10 to the negative 4 newtons per meter. keep it simple for these kind of questions. Lots of people then they sort of then start working out on the other wire, and you can do that. If you work out on the other wire, what you find, or if you let's go back to the equation actually. What you can do is if we take this equation and we say F is BIL, again assuming that they are at right angles to each other, then what you get is this is the force becomes, this is already equation for B, so I'm going to say that's I1, so if I call this wire 1 and this wire 2, so I get I1 multiplied by I2 multiplied by L, and that's actually how I can find the force between two current carrying wires. Now that's actually kind of useful to know, because that's actually how we defined an amp. An amp of current is defined as the amount of current required to have a force of 1 Newton when we have two infinitely long wires with a force of 1 Newton between them when they're 1 meter apart. And there's some pretty cool definitions you can do with that, but again, not needed for CIE. Last one, the current in two wires are not equal. Explain whether the force per unit length on the two wires will be the same or different. So this is actually quite a straightforward one. If we go back to the equation that I wrote, I can say that the force on the wire is mu naught I1 I2 times L, and you notice it doesn't matter which of these is I1 or I2. So straight away, you could just say that the force depends on the product of IX and IY, so it's the same. Or you could say that we know that Newton's third law says that for every action has an equal and opposite reaction. So however much wire X is pushing or pulling on wire Y, wire Y will be doing exactly the same thing on wire X. So the forces will be the same even though the currents are different. That can take a little bit of time to get your head around, so what I'll do in the lesson is give you some exercises to practice that. But hopefully you should have a fairly good understanding of that. If there's anything that you're not sure of, make a note of it now, and make sure that you chat to me about it during our lesson.